In this video, I'm going to explain the method of joints, go through the procedure of how to do it, and then I'm going to give a full example. So to start, method of joints is a method that we can use to solve the members in a truss, and we can follow a simple procedure to do so, and it's step by step. So here's the procedure. First thing, check stability and determinacy. So we want to make sure that the truss is able to be solved by hand. Otherwise, there's no point really in continuing. Determinacy. I have to get better at using this tablet. Okay, number 2 is find zero force members. Now this is really kind of an optional step, because the zero force members will come out in the analysis, but if you can pick out which ones are zero force members ahead of time, then maybe you can save yourself a little bit of work. Number 3 is to determine the slopes or angles of the members. So this is basically just figuring out what the geometry of the system is ahead of time. Number 4 is calculate the support reactions. This is not absolutely necessary in all cases. You could start in some trusses from a point other than the reactions, but the reactions give us a convenient place to start our analysis, so if it were me, I would just start with the reactions all the time. Number 5, we want to find a starting joint. So the method of joints is that we go one by one for each joint in the truss. And so basically one joint we find the forces, those forces can be transferred to another, and then in a step-by-step fashion we go through all the joints in the truss and we find all the forces. So we have to find one starting joint that has 2 or less unknown forces. Because a joint with 2 or less unknowns is a joint that we can solve for. The number 2 is significant because for a single joint in space, we only have 2 equilibrium equations. Sum of F in the x direction equals 0, and sum of forces in the y direction equals 0. Because we can't, in the truss, since all the joints are hinged, we can't have any moments. And number 6, we're going to use a free body diagram at the joint to find the unknown forces. And then once we have those unknowns, we transfer them to another joint. So we then can find another joint with, again, 2 or less unknowns. So the forces that we found in the previous step carry over to other joints, which reduce the number of unknowns at that joint, which means that we can then use the free body diagram to solve it using FBD. Okay? And then step number 8 is kind of the catch-all step, where we continue until the whole truss is solved. Okay, it's pretty simple, a little time consuming. We're going to go through a full example, so you'll see actually how time consuming it can be. Now, just a note before we go forward with the example is that there's 2 ways that we can determine the x and y components of our forces. You can use either slopes or angles. In the example, I'm going to use angles, but sometime in textbooks they use slopes. So what this looks like is if I have a sloped member, a member on an incline like this, with a node at each end, Okay, and then I have some sort of force pulling on it. If I know these dimensions, which I will from the geometry, let's say that this is 2, the dimension doesn't really matter, the unit doesn't really matter here, and let's say this is 1. And we have some angle here, theta. So if we want to use slopes, what we do is we use the slopes to find the hypotenuse lengths. Okay, so we say L is square root of 1 squared plus 2 squared. And this comes out to 2.24. Okay, so therefore our inclined member works on a triangle that looks like this. So we have 1 here, 2 here, and 2.24. Now these are just ratios. This could be 2, this could be 4, and this could be 4.48. So what we can do is use those ratios to find the components. So for example, if we want to find the components, fx, okay, fx is going to be the x direction divided by the hypotenuse times f. Okay, so f is kind of the length of the hypotenuse, and then the x component is 2 over 2.24 times that force in the hypotenuse direction. And likewise, fy is 1 over 2.24 times f. So this is now 1, which is the vertical, divided by 2.24 times f. So this is finding components basically using ratios. Now the alternate way to do it is to use angles. Okay, and this is the way that you might tend to see it in the past. So here we have to find theta first, and theta is the inverse tan of 1 over 2, so that's opposite over adjacent, 1 over 2. And if we do that, we get 26.6 degrees for this example. So now if we want to find the components, we're going to use trigonometry, so we'll have fx is equal to f cos 26.6 degrees, and fy is going to be equal to f sine 26.6 degrees. Okay, so you always got to remember, wherever this root angle is here, the dimension or the component that is adjacent to that root angle, that's the cos, and the one that is opposite of that root angle, that's the sine. So this is f sine theta, and this is f cos theta. And you'll remember that from trigonometry. Okay, so now that we have a kind of overview of the method of joints, the best way to learn it is to do an example. So I've got a sample truss here. We've got 3 meters, 2 meters, 5 meter lengths. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 members at 1, 2, 3, 4, 5, 6 joints. And the first step is going to be finding the determinacy. But we want to find all of the axial force in all of these members using the method of joints. So step 1, as I said, and if you look on the previous, is to check determinacy and stability. Okay, so this one is really easy because it's basically a simple truss made up of nothing but triangles connected together, and it's simply supported. So it's pretty obvious that this is determinate and stable. But we can use the determinacy equation for a truss, which is m plus r, and this is, if it's determinate, it's equal to j. Remember, indeterminate is m plus r greater than 2j. Unstable is m plus r less than 2j. But so let's look, m plus r, this is 9. So we had 9 members, plus 3 reactions, 2 components here, and just a vertical component at the roller. And that equals 12. And 2j is 2 times 6 joints, which we counted, and that equals 12. So therefore, determinate. Okay, and it's stable because our reaction components are not concurrent, they're not parallel, and we don't have any obvious mechanisms here. So step 2 is to find zero force members. Okay, there are a couple rules to finding these. There are no obvious ones here, i.e. if we had 3 nodes at a joint and 2 of them were collinear and there was no external force on the joint, then the third would be a zero force member, but we don't have any conditions like that. Or if there are 2 members at a joint and they're not collinear and there's no force on them, then those would both be zero force members, but we don't have that either. But other thing that we can look at is for rollers like this. So this is a roller, so there can't be any horizontal reaction. So if we were to take f of x about this joint, we would immediately see that this has to be a zero force member. Okay, because it's the only member that's framing into this joint that can provide an x force. And so if there's only one member that can provide an x force, then it has to be equal to 0. So we can say here, since E is a roller, there's no horizontal reaction. So FEC equals 0. So FEC is the force in member EC, which equals 0. Okay. But that member is still required for stability. Okay, especially because if we didn't have this member here, then this would be pin, pin on a roller. So that means that this roller would be free to just move left and right, and we would have an unstable structure. So this is basically just restraining the movement of this roller, but not taking any force. Unless, of course, we put a force on here, then there would be a force that would go directly into this member, if there was an external load. So step 3 is to determine the geometry. Okay, so let's draw out our structure again. It looks like this. Oh, it's a little bit too steep. So let's have something that looks like this, here, all the way across, down like this, vertical member like this, and there we go. Not very nice looking, but there it is. I'm just going to label the nodes again so that we know for reference. A, B, C, D, E, F. Okay, let's put on our reaction forces now explicitly. So this is AY. Okay, here's our external force of 5 kilonewtons. Another external force of 10 kilonewtons. This is EY. Okay, so that's the roller. Now this one's a pin. Usually I would put all of my forces pointing to the right, but since we only have 2 external forces in the x direction, I know that the reaction at A is going to have to balance that 5 kilonewtons. So why don't I just draw it to the left now and save myself some trouble when I'm solving it. So then we have some angles and dimensions. You'll recall that this is 2 meters, this is 3 meters, and these ones are 5. Okay, so now we have some angles. Okay, let's define one angle in here. Let's call that beta. This is the same angle, okay, because this is a symmetric truss. So then if we were to draw kind of a horizontal line here, this would also be beta, if you'll remember from geometry. And then this is a different angle because this is a shallower slope. This is 2 to 5 versus 3 to 5. And this one we'll call it alpha. Okay. We could also show that this is also alpha, right? So if we want to find what these forces are, or what these angles are, sorry, it's very easy. Alpha is inverse tan of 2 over 5, okay, because the height, which is the opposite, is 2. The length, which is the adjacent, is 5. This comes out to 21.8 degrees. Then beta is equal to tan negative 1 of 3 over 5, which comes out to 31 degrees, 31.0 degrees. Okay, so now that we know all of our geometry, we can go ahead and calculate our reactions. And these are our global reactions. So let's start with some MA. I'm going to define counterclockwise rotations as counterclockwise moments as positive. So here we have about A, we have 5, which is turning it negative in the negative direction, which is clockwise, 5 times 3 and 10 times 5, and then positive EY times 10, which is the entire length here. So we have negative 5 kilonewtons times 3 meters, another negative 10, these are the external loads as I said, and then plus EY times 10 meters, which is the reaction, equals 0. Using this we can solve directly for EY, which is going to be 6.5 kilonewtons. Now since this number is positive, that means that it is in the direction that we drew it, which is vertical positive. So I can draw a little arrow here to show that that one goes up. Okay, that's EY. So then sum of FY, positive up. So now we have AY is vertical, that's positive, then negative 10, then plus EY, which we just calculated. So we have AY minus 10, the external load, plus 6.5, which is EY, equals 0. Therefore, AY is equal to 3.5 kilonewtons. And that also comes out positive, which means it's in the direction we drew it, which is up. And sum of Fx. Okay, Fx is super easy because we have only 2. We have one in the positive direction and one in the negative direction. They have to balance each other out. So we're going to have negative Ax, because I drew it to the left, plus 5 kilonewtons, which is the external, equals 0. So Ax equals 5 kilonewtons. And I drew it to the left and it stayed positive. So that means it stayed to the left. Okay, so now we know all of our reactions. So now we have to pick a starting joint. And we want a joint that has only 2 unknowns. And remember, now we know all of these reactions. So we could start over at E. That wouldn't be a horrible place. But I'm going to start over at A here. It's a little bit more complicated. But we have 2 framing members that we don't know the loads for. And we have 2 loads, which are the reactions that we know. So we have 2 unknowns. We should be able to solve all of the forces using equilibrium. So this is step 5 and 6, starting joint. Okay, so we're going to select joint A. Now what I like to do is I just go through all the joints one by one. I draw the joint, I draw all the forces on the joint, and then I can go forward and draw the reactions. So here we have AY, which we know is 3.5 kilonewtons. Then here we have AX, which we know goes to the left, 5 kilonewtons. And then we have 2 unknowns, which are from FAB and FAC. It might be helpful as we're going through this example if you want to draw the structure so that you can look back frequently, because I won't go back too frequently from now on. But so we have this unknown force and we have this unknown force from those 2 members, FAC and FAB, and this is the force in member AC, which is between joints A and joint C, and this is the force in AB, which is between those 2. So joint A has 2 unknowns, and I'm just going to assume when we start that the members are in tension. So members that are in tension pull the joint. So they're always pulling away. So this member I've assumed is in tension, this member I've assumed is in tension. They're both pulling away from the joint. A member that's in compression, as we'll see later, points towards the joint. It's pushing on the joint. Okay, so we can do sum of Fx equals 0. Okay, this is clear. FAC directly balances AX. So FAC is equal to 5 kilonewtons in the direction that we've drawn it, which is tension. Okay, sum of force in the X. Negative AX plus FAC equals 0. FAC equals 5. Plus Fy, okay, remember positive equals up, equals 0. I'll do this one a little bit more explicitly for direction. So up is positive, so FAB, that's positive, plus AY, which equals 3.5 kilonewtons, equals 0. If we solve for AB, FAB equals negative 3.5 kilonewtons. And that negative means that we've drawn this arrow in the wrong direction when we started. So we assumed that it was in tension, but actually it's in compression. So I'm going to say that that equals FAB equals 3.5 kilonewtons, and I'll put a C for compression so that we know for the future that's in compression. Okay, so we've solved both of those unknown equations, and now we can go ahead and move those unknowns to other joints. So let's continue. So now we're on steps 7 and 8, which is continue through the structure for each joint and find all of the unknowns. So joint B is a little bit more complex. We have our joint here. Here's B. We have an external load, 5 kilonewtons. Here, let's take a look at it. So here's joint B. We have an external load. We have FAB, which now we know because we solved it from joint A. And then we have two unknowns, which are BC and BD. And those are at angles. So they're a little bit trickier to calculate. So here's FAB. Oops. Let's try to draw that a little bit more vertical. Okay, this is FAB, which equals 3.5 kilonewtons. And I've drawn that pointing at the node because it's in compression, so it points at the node, at that joint. That arrow is really hideous. I'm going to just redraw it. Okay, that's a little bit better. Okay, and then we have two other unknowns. One is FBD, and this one is FBC. Okay, and then we know these angles. This one is the alpha, which equals 21.8 degrees, and this one is beta, which equals 31.0 degrees. Okay, so this is our whole picture. So now we do sum Fx equals 0, and we get 5 kilonewtons, okay, positive, to the right is positive, plus FBD cos 21.8, okay, because we're talking about the adjacent component to the angle, so this is FBD cos alpha, plus, because they're both in the positive direction, those components, FBC cos beta, which is 31 degrees, equals 0. Now you see right away we can't just solve for one of these because we have one equation and two unknowns. So let's go forward and get another equation from Fy. Okay, so if we do Fy, we have 3.5 kilonewtons, which is our vertical force from FAB that we solved at joint A, and then plus FBD, this time sine 21.8, because we're talking about the vertical component, which is opposite to this angle that we know, 21.8, and then negative, because this one points downwards instead of upwards, FBC sine 31 degrees. Okay, so now we have two equations, two unknowns. We have to solve two simultaneous equations. Which you should be familiar with doing. So let's number this one number 1, let's number this one 2, and we'll start with 1. Okay, so if we rearrange this equation for BD, we get FBD equals negative 5 minus FBC cos 31 degrees, all of that over cos 21.8 degrees, and that equals negative 5.385 minus 0.923 FBC. So I'm just rearranging this equation to get FBD in terms of FBC. So then, in equation 2, I can sub in 3.5 plus, and I know that you probably know how to do this, but I'm just doing it explicitly one time. So I'm going to sub in this equation for FBD into this equation. So wherever FBD is here, I'm going to sub in this part. So negative 5.385 minus 0.923 FBD, sorry, BC. This is FBC. Okay, close. Sine 21.8, and the rest of the equation is the same. FBC sine 31 degrees equals 0. So then if we solve that for FBC, or if I collect all the, I can collect all the parts, so I get 1.5 minus 0.858 FBC equals 0. Then I get FBC equals 1.75 kilonewtons. This came out positive, which means that FBC is drawn correctly, which is in the tension direction, so I'm going to call that tension, and that's FBC. And then if I take that equation, since I now know FBC, and I sub it back into equation 1, then I get FBD equals negative 5 minus 1.75 cos 31 degrees, all divided by cos 21.8. So we get FBD is equal to negative 7.0 kilonewtons. Okay, so that means that the direction that we assumed this to be, which was in tension, was incorrect. It's actually in compression. So this is negative 7.0 kilonewtons, so that means that FBD is 7.0 kilonewtons in compression. Okay. So that's joint B. So now we continue. I'm going to go to the top, so I've done this one and this one. I'm going to go up to D now, because we're going to only have 2 unknowns, because I know this one. Okay, and joint D looks like this. We have, this is FBD, which we just solved, and this is 7 kilonewtons. And it's compression, so it's pointing at the joint. Then we have this, which is FDF, which we don't know, so I've drawn it in tension. And we have this vertical, which is FCD, which we don't know as well, so I've drawn it in tension. And if we take this angle is alpha, which is 21.8, and this angle also is alpha, which is 21.8. So now this one we don't need 2 simultaneous equations, so we're going to start with fx. And we have FBD cos 21.8, so that's the horizontal component of this force, plus, so they're both in the positive direction because they both point to the right, FDF cos 21.8 degrees equals 0. Okay, so these coses cancel out, so we can see that FBD is equal to negative FDF. So FDF equals negative 7.0 kilonewtons, which means that it also is in the wrong direction, so it actually should be pointing towards the node in compression. 7.0 kilonewtons compression. Then likewise, sum Fy we have 7.0, which is our FBD, times sine 21.8 this time, degrees, minus, so that's positive because it points towards up, minus 7.0, sorry, minus negative 7.0 sine 21.8 degrees, minus FCD, which is negative, equals 0. So why is this negative negative? Well, since I'm still doing our sum here, I'd like to keep the arrows going in the same direction and just use the numbers that we've determined so far. So 7.0 sine 21.8 is up, okay? FDF, as I've drawn it, is down, so that's negative, okay? But we found out that the answer to that is negative, so I put another negative here. So I have a double negative, so these are actually adding up. The other way that you could do this is just to look at it, redraw this in compression, realize that these are actually both pointing up, and then it would be 7.0 sine 21.8 pointing up, and then plus 7.0 sine 28 pointing up, because this one actually points up in that case. Okay, so if we solve this one for FCD, we get 5.2 kilonewtons in tension. Okay, continuing on to joint F. You can see that this gets to be a little bit of a long process, but this is the way that it goes with the method of joints. So here at joint F, we have FDF, which we just solved, equals 7.0 kilonewtons in compression, therefore pointing at the joint. We have FEF, which we don't know, so I've just drawn it in tension, and we have FCF, which we also don't know, so I've drawn it in tension. So this is alpha, which is 21.8, and this is beta, which is 31.0. So we're looking at this joint over here. Okay, again, sum Fx equals 0. Alright, 7.0 kilonewtons. Okay, this is the known force. This is now cos 21.8, right? In the positive direction, because it's pointing to the right, minus FCF cos 31.0, because now this is pointing to the left, and we have the adjacent, and that equals 0. So we solve this for FCF, and we get 7.58 kilonewtons. It's positive, which means we've drawn this in the right direction, which is tension. So at least this example provides lots of practice with seeing how the directions work. Then Fy equals 0. I'm going to say positive is up. So now this one is negative because it's 7 down, so we have negative 7.0 kilonewtons sine 21.8. And then FCF is also negative because it points down, right? So we have 7.58 kilonewtons times sine 21.8. And then we also have FEF, which is also pointing down. So we have negative FEF equals 0. Now, of course, like, you can't have all of your forces pointing down. So if this points down and we know it does, and this points down and we know it does, then we know that FEF is going to have to point up to balance it out. So we know that we've drawn this in the wrong direction, and we're going to see that when we solve. So we should expect a negative answer here, and when we solve it, we get negative 6.5 kilonewtons, which is 6.5 kilonewtons in compression. Okay. So now by this point we've actually solved for every single force in the truss, especially if you include the zero force member that we did at the beginning. But if we want to look at another joint, we can look at joint C, which is the one at the bottom here. So we know this one from this joint, 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 we know this one because it was a zero force member that we determined at the beginning. So we actually know all of the forces coming into this joint. So now if we do a sum of F and a sum of Y, we can check, double check that all the forces that we've calculated are actually correct, because they should add up to 0 in both directions. So this is a good way to check if you made a mistake along the way, because you can tell there's tons of different steps and points here where you can make an error. So it's a good idea to check. So let's look at C. We have 5.2 here. We have 5 here. This is our zero force member. This is 7.58. I'll leave it to you to go back and see which members these all are. 1.75, and this is the external load is 10. So we can check sum fx equals 0, negative 5, okay, point to left, minus 1.75. You can get, this is beta, so this is 31, and this is beta, so this is 31 degrees. So this is now cos 31 plus 7.58 cos 31 equals 0, question mark. You work this out, it does, check mark. Okay, same sum Fy equals 0. We have 1.75, this is positive, right? Sine 31 plus 5.2 plus 7.58 sine 31 minus 10. Does this equal 0? Yes. Alright, so we checked and that worked. So we can be confident that the numbers that we came up with were okay. And if we do the same thing at joint E, it's going to be a little bit more obvious because we kind of already did this equilibrium. This is 0. We have our vertical force, which is EY, which was 6.5. That was the reaction we calculated. And FEF, which we calculated right here, is 6.5 in compression, meaning it points at the node. So this is 6.5 kilonewtons. And we can see just from inspection that these all balance out, so that's good too. And so that's the whole truss example, and if we want to draw it, we can draw our final truss with arrows in the right directions. Okay, so this is a little bit crooked. I would advise you, when you're doing this on paper, to use a ruler. So we have A, B, C, D, E, F. Okay, so let's draw all of our forces. Here we have 5. Here we had 3.5. This one points left, 5. We have down 10. And then we can put all of our member forces in here. So FAB was in compression, so that's 3.5. And so what we do is we draw little arrows like this that point at the nodes because they're in compression. 3.5. Okay, FAC was 5 kilonewtons in tension, so we point, arrows point away from the nodes. This is 5. Then FBC, which is this one, was 1.75 in tension, so we draw them away. 1.75. FBD was 7.0 in compression. Point towards the nodes, 7.0. DF, 7 in compression, same. 7.0. CD was in tension, 5.2. CF was in tension, 7.58. EF is in compression, 6.5. And this one is a zero force member, so we can just draw a 0 on it. And that's it. That's the whole truss. So that's the summary. So you might be asked to draw a summary like this because it shows all the members on all the forces on one image. And that's the method of joints.